Welcome, grade 11s. Our next proof is tan chord. And tan chord, this theorem just comes up all the time. Whenever you get tangent, you're probably going to use tan chord. So remember, the idea behind the theorem was that the angle between the tangent and the chord is equal to the angle in the opposite segment. So this chord we just constructed came from P and B. So if we create an angle in the opposite segment, so going from P and B, we're going to get across to angle A. So therefore, what that says is that this angle over here between the tangent and the chord is equal to the angle in the opposite segment, tan chord. And we need to work out a proof for this. Well, let's go for it. I'm going to remove these lines for now, and we'll come back to them. Okay, so what we need to show, let's go, is that this angle here is equal to that angle there. Or that EPT equals B, but we just need to show one of them. So if that angle equals that angle, all our proofs so far, we've constructed radii. There are a whole lot of lovely proofs, and we're just going to stick to doing one for each, although there are definitely two distinct ways of doing this that are quite similar. So I'm going to stick with our radii because that's what's been working well for us. So let's construct some radii. Let me just make them nice here and go, well, I'm going to construct a radius there, OP, because then OPT is going to be 90, and construct a radius across there. So again, constructing radii, and once you've seen the proof, you'll go, okay, it makes sense to do it over here, because look, we've created tan radius, or tan radius, I should say that way. So let's see, by constructing that, this whole angle here is 90 degrees. Right, so TPO, let's write down our construction first, right? Construct our radii, as we seem to always do, because they're such useful things in circles, OP and OB. Well, if that's the case, then angle TPO, that's just an angle between the tangent and the radius, must be 90 degrees, because of tan rad. We've also created an isosceles triangle. That's what we've leveraged quite often with radii. So therefore, if that angle is x, then that other angle up there will be x as well. So let's label these and call this P1 and that P2 and this one B1 over there. So P2, that little angle, we're going to let P2 equal x. Because then we can write down that B1 also equals x because of that isosceles triangle. Okay, so far quite similar to some other ones we've done. We've just added in this tan rad. Okay, well, if that's x and this one here is x, then this angle here from angles in a triangle, try and work it out quickly, or pause if need be. Well, it's just 180 minus those two. So therefore, I'm going to call this O1. Let me put a little spot here. O1, I'm going to say O1 is just 180 minus 2x because of sum of angles in that triangle. Well, if this here is 180 minus 2x, well, that's an angle at a center, and maybe you can see where this is going then. So we've got P and B subtending an angle at the center, also subtending an angle at the circumference, which we're trying to get to, which tells us that this angle here must be half of that angle. Well, that's easy enough because it's just half of each of those, 90 minus x. Okay, cool. So A equals 90 minus x because the angle at the center is equal to twice the angle at the circumference, 2 times angle at circumference. But wait, what are we trying to show? That BPT, this angle P1, is 90 minus x. Oh, P1 is 90 minus x, right? We've already shown that because this is 90 degrees and this angle here is x, so this remaining bit must be 90 minus x. We already showed that TPO was 90 because of tan rad. Well, then we're done. We've shown that BPT is indeed equal to A, with good reason for every statement we've made. So that's our proof. Now, it could be that the diagram looks like that. We don't really have to worry too much about proving it in this way. I'll do it in the next video, but just where we're still going to create our two radii, and we're still going to have a 90 degree here. We just need to think about those, where that 90 and 90 minus x is. But it'll be the same idea. And when we use this theorem, we must just remember it's this big angle here is equal to the angle in the opposite segment. Now you might go, wait, was it B or was it D? Well, D looks a whole lot bigger, but just think back to it's the angle between the tangent. So let me just highlight that. Between the tangent and the chord is equal to the angle in the opposite segment. Well, BP was our chord. So from B and P, we must create the angle in the opposite segment. So it must be that angle over there. Okay, we'll come back to the proof for that one, and I'll see you in the next one.